Hi class, so this lesson is 8.4, the Gay-Lussac's law, temperature and pressure. So we're going to be focusing on temperature and pressure, leaving volume constant as well as the amount of gas constant. This is a direct relationship, so what it means is that when one goes up, the other one also goes up. Now some of these are going to start looking the same. They are not the same. Make sure you understand which variables go with which one. That's why I suggest that you learn Boyle's and Charles. Learn Boyle's first very well, then go to Charles, and then come on to this one so that you can tell exactly what equation, because after a while they all start looking the same. So this one is a direct relationship. One goes up, the other one also goes up, and this is involving pressure and temperature. So if you take a look here, we have a small flame and then it goes into a bigger flame. The temperature is 200 Kelvin and the pressure is 1 atm. But if we increase one of these, which is, let's say, to 400 K, that also results in the pressure also going up. So this is one goes up, the other one goes up. One goes down, the other goes down. So here, let's solve for P2. So this is very similar to the other ones that we can see that we want to remove the T2 from this side. So we multiply T2 and we cross that out. And this results in T2 being over T1, and we leave P, or these would both be together on here. So multiply both sides by T, and that allows us to cancel it out. A gas has a pressure of 2.0 atm at 18 degrees Celsius. What is the new pressure when the temperature is 62 degrees Celsius? So let's take a look at what we have and see what the trend is on this one. So we change everything to Kelvin for the temperature. And if we can't look at the trend for the pressure because that's the variable we want to solve for. So let's take a look at the temperature. The temperature starts at 291 and increases to 335. Since this is a direct relationship, that means that the pressure, we anticipate the pressure will also increase on here. So we plug it in and let's see, we start at 2.0 and we go to 2.3. So at 2.3 atm, that means it has increased. So this follows exactly what we anticipate. So a gas has a pressure of 645 torr. Now we're looking at torr, which we don't handle any differently. At 128 degrees Celsius, what is the temperature in Celsius? If the pressure increases to 824 torr, well, we leave volume and the moles constant. So again, let's look and see if we can determine a trend. And we have pressure at 645 beginning and temperature is 401 Kelvin. Second pressure is 824 torr. We see a trend where pressure goes up. So we anticipate the temperature to also go up. And it does, it goes to 512. Now, this is saying what is the temperature in Celsius. So we actually have to do one more step. We have to take this out of Kelvin, put it back into Celsius. So the temperature for this one will end in 239, which is still, it went up from 128. Okay, now we're going to discuss something different here. Vapor pressure and boiling point. When liquid molecules have enough energy, they will break away from the surface of a liquid. Think of water. It will evaporate away. So if it's an open container, eventually the molecules of the water, all of them, if given enough time, will be able to break away from the liquid and escape. And when it escapes, it vaporizes away. So it evaporates. But that doesn't happen in a closed container. A closed container has nowhere to go. So if you ever left a water bottle, a closed water bottle for a while, and then you see it and nobody's touched it, it's got water droplets all in the inside, even though nobody's touched it, you're seeing water vapor. You're seeing something happening, even though we can't see it. What happens in there is that the molecules still escape from the liquid. However, they have nowhere to go. So they hit the surfaces and they go back into the water. Well, eventually enough of this happens that you have an equal amount of water molecules leaving the liquid and enough equal water molecules from the above the liquid going into the water. So that's what you're seeing happening when you see the water droplets, is the cycle, think of a circle of water droplets going in and out at the same exact time. But if we have, so as a liquid, as it exerts its own vapor pressure. So what happens is these molecules, let's go to talk about evaporation here. I was talking about a closed one, but now I'm going to go back to here. And so what happens is that When molecules start escaping, they create their own vapor pressure. They have to reach a vapor pressure. Oh, actually, it's in a closed container as well. Excuse me. So there's a pressure that's building up as the liquid molecules leave the liquid. And when it reaches a certain amount of vapor pressure, the water can actually start boiling. So we've always taken for granted that water boils at 100, but there's actually special conditions that have to be met for that to happen. So this vapor pressure, this is molecules leaving the liquid, they have their own pressure, and eventually, given enough time and enough liquid to allow this to happen, the vapor pressure will become equal with the atmospheric pressure. And water can boil. So it's not always at 100 degrees. It matters where you are in altitude as well. And so let me explain this. So at high altitudes, atmospheric pressure is lower than 1 atm. Remember, as I'm talking about, the air is thinner above, so you have less molecules hitting you up there. The water will boil at well below 100 degrees Celsius because the atmospheric pressure is not 1 atm. Now, in a closed container, such as a pressure cooker, we increase what would be the atmospheric pressure in a pressure cooker. So water will not boil to well over 100 degrees. That's why some of the food, it cooks a lot faster, because you're increasing the pressure. The water is really, really hot. It's not at just 100 degrees. So let me explain over here. We have vapor pressure. So 760, this is sea level right here. Now remember, as we start going up, then there's not as much atmospheric pressure. There's less molecules bombarding and having collisions. So the pressure is a lot weaker as you go up, because the air is thinner, if you want to remember it that way. So when the water or whatever you're trying to boil reaches the vapor pressure of the molecules trying to escape equals the atmospheric pressure, the water will boil. So if you're at a atmospheric pressure of 270, the water will boil at 70 degrees. And as you start going back down, this is sea level right here, you can see that water will boil at 99, 630, and when you're at pressure 630. So here's an interesting thing I discovered, that in our lab, I've mentioned a few times that I did the lab for this 103 class for five years, I think. And you boil a lot of water in this class, and you're actually supposed to write down and record the temperature of water when it boils. And what everybody in the class has found, that our water doesn't boil at 100, it boils at 99. Why does it boil at 99? Because we're not exactly at sea level. We're actually above sea level. So we have a little bit less molecules hitting us. So the water's going to boil at the atmospheric when the vapor pressure above equals the atmospheric pressure, which is probably around 752. So our water boils at Citrus College at 99 degrees. I have a picture here, gives a better idea of what I'm talking about. So here's this picture, another one. Remember, we are at sea level. So if we're at sea level, we are being bombarded with just all these molecules, but we're used to it. So we don't feel it, except for when you're trying to pop your ears. Now, as you go up, the air becomes thinner, so you don't have as many molecules bombarding you. So the atmospheric pressure is lower than sea level. Now, if you go even below sea level, then the atmospheric pressure is really, really intense. That's why if you go into the ocean far enough, you can just be crushed if you could make it that far down, because there's such an intense pressure down there. But, you need specialized equipment to even make it down to like the Titanic and stuff. So anyways, this gives a good example of it. So at sea level, water boils at about 100 degrees. But as you start going up, and this matches it, so if you look at what matches it here, water boils at 93 degrees Celsius at 6,000 feet. And if you go to 10,000 feet, where even less molecules, it is at, which is really not matching what this is, but pretend it is, it's 90 degrees. And then if you go really high, where airplanes, water boils at 79 degrees. And if you look back at this gives you a chart. So if you pass sea level and you start going down, the water actually has to be way hotter for it to boil. And that's how a pressure cooker works, because the water is so intensely hot, and so is the steam that gives off on it. So here's just again some more pictures. Atmospheric pressure, it will boil at 100. So the water, you can't see the vapor pressure always, but once there's a vapor pressure built up on it, so you see this arrow, then the water will boil. and explain why water boils at a lower temperature in the mountains than at sea. This is pretty much everything I just explained. Atmospheric pressure in the mountains is less than at sea level. So the buildup of pressure above the liquid, which is now we consider vapor because it evaporates away, it has to build up a certain amount of vapor pressure above that. Once that vapor pressure reaches the atmospheric pressure around it, it will boil. And depending on the altitude, that's going to determine the temperature that will lead to that boiling. Hope that makes sense. Okay, that's it.